Thank you. Thank you for being here. Welcome, everyone. My name is Alberto Garcia, and I'm going to talk about a new tool that I'm writing that is called Dirlock. I will start by introducing myself. I'm a software engineer at Igalia. During the long history of the company, I have been working in many different projects. Some examples are GNOME. I was involved in the GNOME project for some years. I was also working in the Maemo Amigo projects. Those were the platform made by Nokia to create a series of mobile devices running Linux. And then more recently, I've been involved in the QEMU project, where I was working in the disk I/O layer for many years. I'm also a Debian developer. I've been using Debian basically all my life, but I'm also contributing to the project, and I've been an active developer for many years. At the moment, I'm working on SteamOS. That's the operating system of the Steam Deck. So today I'm going to talk about a new tool called Dirlock. It's, as the title of the presentation says, it's a tool to manage disk encryption, but it's not a new encryption system. I'm not designing a new encryption system, something that has never existed before. This is a tool to manage already existing technologies. So I'm going to explain why I wrote a new tool and what's the use case. So this started during the work for SteamOS. That's the project that I'm working on. As you know, the Steam Deck and other devices that are running SteamOS are portable devices. They are easy to lose. They are easy to get stolen. And at the moment, if someone takes control of your Steam Deck or similar device, they can read the contents of your hard drive because they are not encrypted. In principle, it maybe doesn't sound like a big deal because they are machines used for gaming mostly. So, I mean, you lose your games. But there's still some personal data there. You have your you can also have third-party accounts apart from the Steam account. And they are generally not just consoles. They are really general-purpose computers. You can install software there. You're actually encouraged to install your applications and do other things. So it comes with a desktop mode where you can do normal computing. So having some kind of encryption was a feature that some users have been requesting for a long time. Briefly, the disk layout of the Steam OS is based on an AB system. So there's two sets of partitions for the operating system. Those big ones called A and B in the graph. That's the root file system. That's basically the operating system. That's a read-only file system. And the information there is public. It's basically downloaded from the internet, and there's nothing confidential there. Then there's a couple of smaller partitions for the /var, where you keep some system state, etc. But the bulk of the disk is used for the home file system. That's what you see there. And the home file system is what holds, the home directory is what holds pretty much everything that the user does, all the games and all the configuration, etc., as usual. But being the only really large partition in which you can store data, there's also some files that would normally belong to the /var, maybe, but are stored there for convenience. So that's where most of the data is. And the size of the partition changes depending on the model of the device. Like in this example, this is 64 gigs, but it can be much larger. Currently, the alternative that users have is the Plasma Vaults. The machine ships a KDE desktop. So Plasma desktop has a feature called this vault. Allows you to create protected directories where you can put your personal files there, and then you lock them with a password. And then when you need to access them again, you enter the password, and you unlock them, and you can use them normally. This is very easy to use. It works fine, but it's not a general-purpose solution for encrypting the whole file system or the whole directory of the home directory of the user. So with this in mind, we're thinking about the goals, the basic goals that the encryption system should have for this use case. And although these goals were designed with the needs of SteamOS in mind, the idea is to make them general enough so they can be used in any Linux system or in other systems. The most important one, and that's why I write it in bold, is that if you lose your computer, if you lose your machine, your deck, whatever you have it, your personal files should be unreadable, should be protected. So that's the main use case. There's many other types of attacks. There's the so-called evil maid attacks. Those are also considered, and those are important, but the main one is the one that is involved here, that if you lose your machine, no one can read your files. So for that, at least, the home directory should be encrypted, the complete home directory. It would also be nice to be able to encrypt other directories because, as I said, the partition also holds other kinds of data. Also, this machine has removable drives, so people move SD cards with libraries of games and maybe other data. So having the possibility to be able to encrypt that is also a plus. Also support for multiple users. At the moment, this is not a thing because SteamOS only is a single user machine. There's only one user. But if in the future there's a decision to have more user accounts, it would be nice to have multiple user accounts with independent encryption keys. So even if one account has a weak key, then the others are not compromised. And access should be authenticated. The user, when they try to use the device, they should be entering some kind of authentication method, a PIN, a password, or something similar. One thing to note here is that we are talking about, although this is tries to be a general purpose system, this was designed for a handheld device that doesn't have a keyboard. So the expectation is that users are going to use passwords or pins that are not cryptographically strong. They are going to be weak, like short pins, like similar to what you have in a mobile phone. So the encryption system should take that into account. So having support for hardware-backed mechanisms is something interesting to have. And then, especially since this machine has been these devices have been in the market for years, it would be nice to have a way to enable encryption without having to reinstall the whole operating system from scratch. From the security point of view, I know that this is not ideal. Ideally, you should encrypt everything first and then start to put your data. But we want to be able to allow users to do that and then maybe start putting their secret data, or they decide what to do. But we don't want to force users to wipe the whole hard drive and then install everything again. So ideally, a simple button or command to encrypt the data would be the best thing. And for that, it's also handy to have a DBAS API in order to be able to manage the encryption system. And last, the system should have a reasonable performance. Like adding disk encryption, there's always some overhead. But let's try to find something that is not too slow so the user can use the machine normally without noticing a very big regression in performance. With those goals in mind, there's basically 3 big categories of encryption technologies. The first one, I mentioned it already, is stack file system encryption. That's basically, the way it works is that your files are stored as regular files on the hard drive that you can open with any program. But the contents are encrypted, and the names of those files are also encrypted. So you don't know the names of the files, and you don't know what's inside. And in order to have access to them, you mount that directory onto an empty directory, and then you can see the data and have access to it. Examples of this technology are EncFs and gocryptfs. They have very similar purposes. EncFs is a bit the older one. It's considered not secure anymore, so even the developer recommends to use gocryptfs. These are implemented in user space using Fuse, which is very convenient, but has the problem that it's not so performant. This is already shipped by the system. It's used by the Plasma Vaults tool that I mentioned earlier. But this is not a good solution for encrypting the whole system. The other category would be block device encryption. That's the most popular these days, I think. This encrypts complete devices, partitions, or loopback files. And it works at the block level. So it encrypts separate blocks that doesn't care about what's inside. You would normally put a file system, but in principle, you can put anything, really. This offers the best confidentiality because what's inside is completely hidden. You don't have an idea what's inside. You don't even know how much data is being used. You know the size of the partition, so you can, but you don't know if it's full, if it's empty, if it's, you don't know what's inside. In Linux, the most popular implementation of this is Lux, or Lux. I will say Lux, sorry. And in Lux, the header contains the encryption keys. So when you want to unlock the volume, you need to get the encryption keys from the header, and then you are able to use the volume. And last, the third type of encryption system is native file system encryption. In this case, the files are encrypted directly at the file system level by the kernel. This offers some flexibility because a file system can contain a mix of encrypted and unencrypted directories. So you don't need to pre-allocate space for your encrypted data. You can play with that. You can use all the available space organically and use it for encrypted data and unencrypted data as you need it. Has the problem that it only offers partial confidentiality. The file names and file contents, those are safe. But the metadata is not safe. Like you can see the file sizes, you can see the permissions, and things like that. In Linux, this is implemented by the fscrypt API that is provided by the kernel. but then each file system needs to implement that API in order to offer encryption. At the moment, it's implemented by ext4, f2fs at least. I think there's work for better FS. I don't know what's the status, but I suppose it will be available soon. And fscrypt is just a kernel API. You give the kernel your encryption key, and the kernel takes care of keeping your files encrypted. But user space is responsible for managing those encryption keys. So that's completely up to user space. The kernel doesn't, the API is not concerned about that. So with those, after these categories in mind, basically the decision is between Lux and fscrypt. Lux, as I said, has the benefit that offers the maximum confidentiality and protection. It also supports hardware-backed mechanisms like TPM, FIDO tokens, etc. Systemd implements that, but Lux is designed so additional mechanisms can be added in the future. It has a bit of some problems. Usually, not always, but depending on the case, but usually it has to be unlocked early on boot. So that can limit a bit the choice of authentication methods, the choice of input methods, and the kind of UI that you can offer to the user. It also, since it requires you to pre-allocate the space for the encrypted data, you don't have a fine-grained control about what to encrypt and what not. Because of that, it's also hard to encrypt an existing installation. You normally need to wipe the partition and start all over again. You don't need to necessarily wipe the whole hard drive, but you do need to remove the partition or start it again with making it encrypted. On the other hand, fscrypt makes it very easy to encrypt an existing installation because you can start from an existing file system and start encrypting directories there. And it also makes it very easy to encrypt multiple directories for different user accounts or other directories that are not user accounts with different keys. It's very easy to integrate with PAM, so any authentication, most authentication systems in the Linux world use PAM, so they will work automatically. And it also can be, it's very easy to unlock it after booting. You can even do it remotely using SSH or something similar. The problems is what I said before. I mean, there's more problems, but one of them is that the metadata is not encrypted. So you can get some information about what's there. For example, you can know the size of the encrypted data. You can even see the approximate directory structure. So if you know what's there, you can kind of guess what's inside. For example, in the case of SteamOS, the contents of the .steam directory are well known, like the structure at least. So you can kind of guess, even if the directory is encrypted, you can kind of guess how many games are installed, the size of each game. So you can even guess what games they are because of the size and the number of files, etc. And as I said, also the permissions, timestamps, etc. And also attackers can delete files. Doesn't offer protection against an attacker deleting files. You cannot open the files because they're encrypted, but if you remove them, a normal unlink call, they will remove them from disk. All things considered, and I thought that for the use case, fscrypt offers a better solution, more practical. It offers confidentiality guarantees that are good for our main use case. It's also flexible. It's very easy to enable it in existing systems, so people can start to test them in their devices without having to reinstall or lose their data or anything. And it also offers good performance. In my tests, it was performing a bit better than Lux even. The thing is that fscrypt is just a kernel API. So we need to handle the encryption keys in user space. The kernel gets a master encryption key, and you are responsible for taking care of them. And for that, there's different implementations, and they are all incompatible with each other. The existing tools that I was evaluating was, first of all, the one tool called fscrypt as well, confusingly enough. It's related to the fscrypt kernel API, but it's different. So you can, it manages the metadata, etc. But you can use the kernel API without using this fscrypt tool and its file formats, etc. And then there's the systemd Home project that I'm going to mention now in a minute. Starting with the fscrypt command line tool, this is the reference tool to manage encrypted directories. It was written by Joe Ritchie and Eric Biggers from Google, which are the same people who were working on the kernel part of the API. So those are the people who know best the system. It was written in Go, and it's very simple to use, covers all the functionalities of the API, and it works great. It has PAN support, so you can use it to unlock to protect your home account. But it doesn't offer any kind of, it only allows passwords and raw binary keys. So it doesn't offer more advanced mechanisms for authentication. It also doesn't offer any kind of DBoss API. It's just a command line tool. Then there's systemd homed. Systemd homed is primarily not an encryption tool. It's a tool to manage human user accounts. And the focus on human user accounts is systemd homed doesn't concern itself about the accounts that are available in any Unix system that are for system services, daemons, and things like that. It's only for accounts that are actually for humans that have a home directory, and humans logging with a password, etc. And the idea is to make those accounts portable, to separate the account configuration from the general system configuration so you can move them from one machine to another. They talk about, for example, having your account in a removable drive so you can move it from one computer to the other. So that's the primary goal of this project. For storing the home directory, it offers several storage backends. 2 of them are encrypted. One of them uses looks, and the way this works is that they create a loopback file in the home partition. They format that file with looks, and inside the file, inside the lookback, the encrypted volume, there's a new file system that represents your home directory. The other storage backend is fscrypt. Unfortunately, they use the old and deprecated version 1 API of fscrypt that is not suitable for us, although adding support for the version 2 would be, in principle, doable. Systemd homed also has other nice features. They have the DBoss API. They support PAM and FIDO, but they don't have TPM support. One of the problems is that it's primarily not an encryption tool, as I said. So the goal is to make portable user accounts, and for that, they make some design decisions that are a bit can be a bit complicated. For like they offer some external additional functionalities that we are not interested in our case. First of all, it encrypts the home directory and nothing else, and we would like to be able to have the chance to encrypt other directories. It also, the user database is not in etc passwd because they consider that that's system configuration and that's separate from user configuration, which is a very reasonable proposal. But for games, we have to run games that are not all of the games like that. I can go into details later if you are curious. They also use ID mapped mounts. When you mount your home directory, you don't have the full range of user IDs and group IDs, which in general is what you get is perfectly usable for most purposes, but there has been interactions with some projects. For example, with Podman, there have been cases where the defaults used by Podman in most systems conflict with the defaults used by systemd homed. There are a few hurdles, but otherwise it was a strong candidate. However, all things considered, we decided to implement a different tool that focuses only on encryption. And this one is called Dirlock. As I said, it does encryption, authentication, and nothing else. Doesn't touch anything else. It tries to be as least invasive as possible. It's heavily inspired by the fscrypt command line tool, partly not only in the terminology and overall design, but also the encryption methods, etc. I tried to not to divert from those. I tried to keep us where it makes sense to keep compatibility, let's say, with those. So maybe in the future we will be able to provide a tool to convert the metadata from one to the other, for example. And the tool is under development. It still is not in production state yet, but it's usable and people are already testing it. PAM support is working. FIDO support is working. There's some basic TPM support working. The way we use TPM is what I said earlier last year. We are going to use this in a machine that has only a touch screen. We are expecting users to have very low entropy passwords. So the TPM offers an anti-hammering mechanism that prevents brute force attacks. So that's the first reason why we're using the TPM. And then we have also the DBoss API, although that's at the moment in prototype stage, so it's really not ready for general use yet. The code is open source. It's free software, published under the BSD license. It's available in the GitLab of the SteamOS project. You can find it there. It was written from scratch. It's written in Rust. It was written, as I said, with SteamOS, with the needs of SteamOS in mind, but it should work in any Linux system. There's nothing specific to SteamOS in the code, and it should work. It's a general purpose tool. And those of you using SteamOS in the upcoming 3.8 release, it will be available as an experimental feature for users that want to test it. It's an opt-in thing. Users who are already testing the development image of SteamOS 3.8, they are already testing it, so we are already getting feedback from them. And now I will mention briefly the basic architecture. In fscrypt, each encrypt directory has an encryption policy. And the encryption policy contains the master encryption key that is used to protect the data, plus several other parameters, including the encryption algorithm and other things. So you load the master encryption key into the kernel in order to unlock a directory. So once you load the encryption key, you can see the files and you can use them normally. And when you remove the key from the kernel, you cannot see the files anymore. As I said earlier, user space is responsible for managing that. So the kernel doesn't concern with those things. You have to keep the master encryption key safe. What we do is we don't use the master key directly. We protect it with an intermediate key called protector. And there's different types of protectors. We have a password protector for normal passwords. There's FIDO2, and there's others. This offers more flexibility, like we're going to show some examples, but also has the benefit that if a protector is compromised because a password is lost or something, it can be deleted without exposing the master key and without having to re-encrypt all the data. The basic design and even the terminology is taken from the fscrypt tool, but the basic idea of having intermediate keys to protect the master key is a much older thing and has been used in Lux and BitLocker and other tools. In the case of Lux, the header doesn't store one copy of the master encryption key, it has several copies of the key, and they are encrypted with intermediate keys that are generated using the user password or other mechanisms. Version 2 of Lux has some additional fields called tokens, where you can have additional information that you can use to retrieve the intermediate encryption key from other devices. For example, the TPM, FIDO tokens, PKCS, etc. BitLocker has a very similar idea. Of course, the implementation's details change a bit and the specifics, etc., but the basic idea is the same. You have the master encryption key. They call it differently, but you have different ways to unlock it. In the case of Dirlock, we don't have only one master key. We have several because we can have several encrypted directories. So this changes a bit the possibilities. For example, imagine that we have two home directories from two different users. Each one of them has a password. So each user can unlock their directory with a password, but you can have them an additional protector. In this example, is a FIDO protector, which can unlock both directories using, in this case, a FIDO token. This can happen regardless of whether the users change the password or not. The passwords are not affected. Users can modify the password normally, and the FIDO protector works the same. Another possible scenario is that we have, again, two different user accounts with two different passwords. They are independent from each other. They have different master encryption keys. And then there's a third directory that is shared by both users. So both of them can unlock that directory with their passwords. They don't need to know information about the other user's password. They don't need to have a common password. So the system works. In terms of protector, we have a few implemented. The basic one is the password protector. The way it works is that the password entered by the user is mixed with a salt through a key derivation function. You get an intermediate encryption key, and with that, you unlock the protector key. In the case of FIDO, the intermediate encryption key is generated by the FIDO token using a credential and a salt that was previously generated. And in this case, the ping is optional, and it's used to authenticate, to tell the token that you are the person who is authorized to use it, so they give you the key. If you don't use the ping, then the token only requires that you confirm your presence, like physically touching the token, in order to get the encryption key. And finally, there's the TPM. In the TPM, we get the protector key directly from the TPM. The TPM takes care of keeping it secret. And here, the ping is only used for authentication as well. In addition to that, the TPM also allows authorization policies that allows you to authenticate using a different mechanism. Authorization policies can be very complex, but the way they are typically used in these systems is using the PCR registers. The PCR registers are registers that represent the state of the machine, various components of the machine, including the firmware code, the kernel, the bootloader parameters, etc. So you can do it so if the system is in a well-known state, then the TPM gives you the key, and if it's not, if it has been tampered with, then you don't get the key. We don't implement this at the moment. We may do it in the future, but at the moment, this is not there yet. Then the commands themselves, they are very easy to use. I think you can encrypt a directory, then lock it and unlock it, and then you can create additional protectors, and you can attach them to an encryption policy or remove them from an encryption policy. I will show an example in a minute. This also has PAM integration. There's a module called Dirlock. And again, the idea was to try to make it as least invasive as possible, so you don't need to convert users to do anything like that. The way it works is that if a home directory is encrypted, then this PAM module takes care of it, of the authentication. And if it's not encrypted, then it returns user unknown and is passed to the next module. One possible way of implementing this is this one. In this example, if the PAM Dirlock module comes first for authentication, so if the user account is encrypted, PAM Dirlock takes control. If the authentication succeeds, then the user is granted access. If the authentication fails, then the access is denied immediately. And if the user is not known because it's not encrypted with Dirlock, then the next module takes control. For passwords, this is the same idea. If the home is encrypted, then we change the password in the protector. If it's not, we pass to the next module. In this example, what we do is that the passwords are actually, the Dirlock takes control of managing the passwords. So the passwords are in the protectors. So the password is in etc shadow is not longer necessary. You can actually disable it. But if you want to have it, to keep using it, and you have to have your password also there, you can configure PAM differently. So you have the passwords in both sides, and when you change it in both sides. So they have to be kept in sync, but if you configure everything correctly, it should work. And now I'm going to show a short demo. For this, I have a virtual machine. This is running a standard installation of Debian. This is the latest stable version. It's Debian 13. And it has a, user account called guest with a normal password. It's a normal account. There's nothing special about it. I will SSH into the VM. And if I have a look at the user account, you see the normal contents of a user account. There's nothing special. This account is not encrypted yet. If I run Dirlock status, it will tell you that it is not encrypted. So I'm going to encrypt it now. So I will use encrypt. And I'm going to use a TPM protector. This is a VM, but it has a TPM support using a software TPM. So TPM2 type. OK, it tells me that the directory already contains data, so I need to type force to confirm. I need to enter a new ping. And this is the ping. This ping is basically the password that I'm going to use for authentication. And now the directory is encrypted and with this new policy. The contents are still visible because the directory is encrypted, but the key is in the kernel, so it's unlocked. But if I lock it, then the contents are no longer visible. This is what you get. This is what you would see if you take a hard drive that has been encrypted with fscrypt. If you try to open any of those files, what you get is error because the key is not available. But other than that, you can see the metadata, as I said earlier. You can see the sizes, the permissions, etc. Now, in order to unlock the account, I can use the unlock command. Then I will need to enter the ping of the TPM, and it will unlock it. If I enter a wrong ping, I can enter it a few times. And you can see that it says 8 retries left. What we do here is the TPM has an anti-hammering mechanism, so it allows a maximum number of failed authentication attempts before it locks out for a certain amount of time. So what we do in the lock is we keep track of that number, and if it goes under a certain level, we show it to the user, like, hey, you have X number of attempts left. We're going to now add another protector, this type a FIDO protector. I have here a FIDO token. This is a YubiKey key. I'm going to connect it to my laptop. And now I'm going to make it available for the VM using USB pass-through. So if everything went fine, it should be visible here. There it is. So I will create a protector. And in this protector, I can decide whether I want to have a ping for authentication or not. So I can say use ping false, and I protector type. I create. OK. I need to enter the ping first in order to generate a credential. So if I do it, I need to confirm the like touch the token physically, and now the protector is created. So you can see the encryption policy. This one is using the only available protector was the TPM one, but now I want to use the FIDO protector also with this one. So Dirlock policy add protector. So to this policy, I'm going to attach the new FIDO protector. So I need to confirm presence, meaning touching the YubiKey physically. Now I enter the system protector key, like in the case of the TPM. And this has been added now. If I run status, then I will see that this is available with both protectors. Now if I go to GDM, if I try to log in, the system detects that the FIDO token is available, and it tells me confirm presence on the token. So if I touch it, it logs in normally. Now I can log out. And if I remove the YubiKey, I can do it in the VM in this case. Now it's not visible in the VM anymore. And if I try to log in, the system detects that the YubiKey is not available and asks me for the TPM pin. So I enter it. And it should work. There it is. And now I'm logged in. This is, as I said, implemented with PAM, so I don't know if this is visible. Yeah. With the typical passwd command, I can change the TPM pin here. I can put something else. And that's it. And that's basically it. As you can see, the usage tries to be very simple. And this is what we have at the moment. So this is all, I think. So if you have questions, comments, or anything, I will be happy to answer. So for the project itself, the plan is to be only command line. There will be some API, DBus API, so you can actually encrypt the directory, etc. But for the case of Steam, that's not part of my work. I will offer the API so they can decide the best way to integrate it. Yeah, I don't know if there's a microphone for like there's a person, the person in green there. Oof, sorry, I cannot really hear you from here. Sorry, I didn't get the last part. With GDM. So in the Steam Deck, at the moment, there's auto-logging. So you turn on the device and you go directly into your user account. What we do at the moment for people who are testing it, because this is still experimental, is the Steam Deck uses SDDM, which is I think the KDE version of the GDM. So if it detects that the home directory is encrypted, then it shows you the logging, the usual logging screen. Then you enter your data there, and that's it. And if it's not encrypted or if it's not locked, then it does auto-logging normally. Yes?
Is the anti-hammering per file or per directory that's locked?
So the anti-hammering mechanism of the TPM, this is actually a global mechanism for the TPM. So this is a bit tricky because this is just one anti-hammering mechanism for the whole system, which makes it, I think, unsuitable for some use cases, but I think for the Steam Deck it makes sense. So yeah, so when I change the password, I change the TPM pin. The TPM, that's the question. Yeah, the TPM pin, despite the name, the TPM pin is not actually stored in the TPM. The TPM pin is part of the key that you generate. So it's attached to the specific key that you want to decrypt with the TPM. So you can, with the TPM, you can protect different secrets, different keys, or different files, or whatever, and each one of them can have a different pin or password. So those are not global passwords. And the question is if we can give names to the policies. No, I think at the moment we don't have names to the policies. The problem with the policies is that, I mean, we can do that actually, and that's usually what you can do with fscrypt is that you can go to a directory and ask what the encryption policy is. The way it works with fscrypt is that you cannot tie a policy to a specific path, because if you move the directory to another location, the policy is still the same. So you cannot really. I could store on this is the policy for this directory, but if the user moves the directory, then the policy is still valid, but it's for a different directory now. But the protectors do have a name, though. I understood the part of the network file system, but. Yeah, so once a file system is unlocked with the fscrypt, this is a general fscrypt thing. This is not actually not directly related to what I did, but once it is decrypted, it can be used normally like any other directory of the file system. There's no restriction at all. And this is actually a thing with the version 2 of the fscrypt API. Version 1 that I mentioned earlier that is still used by systemd Home has additional restrictions in that the encryption key has to be part of the user key ring, if I remember correctly. So you can have situations where the user has access to their home file system, but the root user doesn't have it. So that can be a problem. And in this case, now with the API that we are using, as soon as it's unlocked, then the regular user Unix permissions apply, and you can see with what those permissions allow you to see, that's visible.
Are the fscrypt performance characteristics appropriate for most gaming situations?
In our test, or in my test, yes. But as I said, we are still testing it, and users are testing it, and we haven't noticed anything remarkable. So, yeah. I don't know, I'm not an expert in that, but I don't think that disk I/O is the bottleneck in general in games. No more questions? Well, there's one. Please. So the question is that the fscrypt allows attackers to delete files or directories even if they're encrypted. And the question is whether that's something that we plan to address or if it's code that we plan to live with. I would say that we plan to live with that. There is, I haven't evaluated it very closely, but there's modules like DM integrity, etc., that allows to have integrity in an otherwise normal file system, but I haven't. My early, let's say, impression is that it has some additional performance overhead that maybe we don't want to use, but we haven't got to that yet. OK, now I think we're done.